Hey guys, welcome back to chapter 10. We are going to talk about our last property that is affected by intermolecular forces. It's going to take us a little time to build to it. We're going to talk about vapor pressure, but it's going to take us a minute to build to what is vapor pressure, like what causes something to have a high vapor pressure or a low vapor pressure. Once we understand vapor pressure, then we can talk about how intermolecular forces affect that. So before we get to vapor pressure, let's first talk about the vaporization process. So vaporization is that process when a liquid becomes a gas. So we talked a little bit about this with boiling. Some of the things are going to hold true, be the same. Some things are different. When we're talking about vaporization, we're talking about molecules that escape this liquid phase and become a gas. Now, in order to do that, just like in boiling, we have to overcome those intermolecular forces that are holding those particles in the liquid phase. So we have to have enough energy, specifically thermal energy, to overcome those intermolecular forces, which allow a state change, allow those particles to be released as the gas phase. So remember, liquid particles very close together, lots of interaction. Gas particles, little to no interaction between those particles. So we have to overcome the intermolecular forces. Okay. The big difference here is for boiling, because we were at such a high temperature, we could have a molecule that was down here in the bottom of the beaker become a gas. We could have a molecule up here at the top of the beaker become a gas. Because we've increased that temperature so much, any of the molecules are available to us. Vaporization is a little bit different, okay? So think about this as evaporation. And we're going to talk a lot about this in the lab. Evaporation may happen at room temperature, right? We have this vaporization process happen at room temperature. Because of that, during the vaporization process, only the particles at the surface are available to vaporize, right? Because we're at room temperature, a much lower thermal energy, we don't have access to these particles in the bottom of the beaker, just the ones at the surface. So that's the big difference between vaporization and boiling. But you can still think about that. We have to overcome these intermolecular forces in order for that particle or that molecule to become a gas. Now, there's a number of things that can affect this vaporization process. So what are some things that can affect the vaporization process? Well, certainly temperature is a factor. If we increase the temperature, we're going to increase the kinetic energy of those particles, right? They're going to move faster. And we're going to see more of those particles have the ability to release into a gas. So as we increase temperature, we'd see this vaporization process increases. If we decrease the temperature, particles are going to move slower, less of them are going to vaporize. So certainly temperature is a factor. Surface area is also a factor. So if only the particles at the surface are available to vaporize, if we increase that surface area, that's also going to increase the number of particles that are available to vaporize. So think about if I set a beaker of water on the counter, or if I took that same amount of water and I dumped it out over the whole area of the counter, which one of those two samples would evaporate faster? The one that's spread out is going to evaporate faster. And that's just because more particles are at the surface, so we would see more of them vaporize than in that beaker. There's only just a teeny tiny number at the surface. Now, the last thing that we want to talk about that can affect the vaporization process, we want to talk about intermolecular forces. So that's the one we're going to focus on here. So we're going to talk about the strength of intermolecular forces and how that affects the vaporization rate. So we've got these particles the surface of this container, right? In order for that particle to release and become a gas, we have to break those intermolecular forces. Thing that has a very high intermolecular force, right? So we're going to increase that intermolecular force here. So maybe this is a water molecule that has this hydrogen bonding, really strong intermolecular attraction, or it's a polar molecule that has this dipole-dipole moment, very strong intermolecular attraction, right? Do you think those particles are going to be more, or are going to be easier to vaporize, right? Pop them off? Or do you think it's going to be harder to vaporize those particles? So with an increase in intermolecular forces, we are going to see a decrease in that vaporization process. Okay? So the stronger the intermolecular force, the less likely those particles are going to be to release, the less of them that are going to be released. So we've got to overcome this really strong interaction. It's probably not going to be easy to do that. So if we increase the strength of the intermolecular force, we're going to decrease the strength of that vaporization rate. Now let's think about the opposite scenario, right? So let's think about something that has a really weak intermolecular force. So think about some of those organic molecules where the strongest intermolecular force is London dispersion. That's it, right? A bunch of nonpolar molecules. So if we decrease the intermolecular attraction between the particles, now if we think about the vaporization process, it's going to be a little easier for those particles to release. There's not as much holding on. They're fleeting attractions that's holding them in anyway. So the moment that that attraction doesn't exist anymore, boop, those particles can pop off and vaporize. So if we decrease the intermolecular forces, that's going to increase the vaporization rate. It's going to be easier to pull them off. So we're going to see more particles will vaporize. So that is three effects, or three things that can affect vaporization. So temperature, increase the temperature, increase vaporization. Area, increase surface area, increase vaporization. So both of those are direct, up and up. Intermolecular forces, we increase the intermolecular attraction. That's going to decrease the vaporization rate. So we see that one is indirectly or opposite, right? So that's vaporization. We haven't yet talked about vapor pressure. We've just talked about vaporization. So now let's talk about this and start to expand it to vapor pressure, right? So here we've got an open container. That's what we've talked about so far, right? So in an open container, vaporization will continue until all of that liquid is gone, right? So particles at the surface become a vapor, they go away. Next set of particles comes to the surface, they vaporize, go away. Next set of particles go away, next set of particles, so on and so forth. So we would see the line in this container, we would see it continually decrease if this was an open container, right? It would just continually be converted to vapor. But to talk about vapor pressure, we've got to close this container. Okay? So when we have a closed container, the vaporization process will begin. We've got all liquid, every single particle is a liquid particle. Some of those particles are going to start to evaporate. They're going to start to become a gas. So if I'm first beaker here, we've got all liquid. The only direction for those particles to go is up into a vapor. And this process is going to continue to happen for a while. Vapor, 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 vapor. Then we're going to reach a point where we're holding as much of that gas above the liquid as we can possibly hold. So we've kind of saturated this area above the liquid. And what we're going to find is all of a sudden, the counter process is going to happen. One of those gas particles is going to condense back down to a liquid. So we might have vapor, 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 liquid, vapor, 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 liquid. So we're going to start to see the counter process happening more and more. Then we're going to reach this state of what's called equilibrium. We will talk at length about equilibrium this semester. So here's a great place to introduce it. So equilibrium in this scenario is going to be when the rate of vaporization equals the rate of condensation. So it's a dynamic process. We still have molecules that are becoming vapor. We still have molecules that are becoming liquid, but they're happening at the same rate. So it may look like this. 2 particles become vapor. At the same time, 2 particles become liquid. 1 particle becomes vapor. 1 particle becomes liquid. 3 vapor, 3 liquid, so on and so forth. So the rate of evaporation equals the rate of condensation. We are at this dynamic equilibrium. It is at that moment that we can begin to measure vapor pressure, okay? So the maximum amount of gas particles that can be held above this liquid, we can then reach in and measure what is that pressure that those particles are exerting. Once we've reached this state of equilibrium, the following statements are true. Equilibrium has been reached. The number of gas molecules in the gas phase does not change. 1 becomes gas, 1 goes down to liquid. 2 become gas, 2 become liquid. So if I were to take a snapshot of how many particles are in the gas phase, that would not change from snapshot to snapshot. It remains constant. We now have a pressure exerted by that constant gas phase particles, right? So there's a pressure exerted by the vapor over that liquid. The pressure exerted by that vapor over the liquid is called vapor pressure. Okay. That is called vapor pressure. Now, we understand vapor pressure. We understand vapor pressure is the number of particles above this liquid. How does that relate to intermolecular forces? This slide is just saying in words a lot of what I've already said, so I'm just going to click through it, read it on your own time to really understand this dynamic equilibrium, but I've said all these things already. So intermolecular forces and vapor pressure. The number of particles above the liquid is going to determine the vapor pressure. Now let's think about how vapor pressure would be affected by intermolecular forces. So something that's going to have let me get my pen out here. So something that's going to have an increased vapor pressure, okay? So increased or high vapor pressure means there's going to be a lot of particles over this liquid. Lots of particles exerting a high or greater pressure. What would result in a lot of particles being over the liquid? Do you think that's going to be a substance that has strong intermolecular attractions, or do you think that's going to be a substance that has weak intermolecular attractions? If there is a weak intermolecular attraction between these particles, they will more readily become a gas. So we're going to see a larger portion or a larger number of these particles that become a gas. They break those intermolecular attractions, they become a gas, and that will increase our vapor pressure. So the weaker the intermolecular force, the higher the vapor pressure is going to be. There's going to be more particles up here as a gas. I'm going to erase this so you can see the words. I like to use a lot of symbols. That helps me. But here's the words. The weaker the attractive forces between the particles, the more molecules that will become a vapor, the higher the vapor pressure is going to be. Conversely, if we observe a decreased or a lower vapor pressure, that is going to be because the intermolecular forces that are holding those particles as the liquid have increased. So the stronger the intermolecular attraction, the less likely they're going to be to become a vapor. So they're going to stay in the liquid phase, not be as likely to become a vapor. So we're going to see a lower vapor pressure. Less particles release, the pressure is going to decrease. Okay. So there's my symbol. Let's take a look at the word version. So the stronger the attractive forces between the molecules, the less molecules that will become a vapor, and the lower the vapor pressure is going to be. So, again, what we're going to see here is that inverse relationship. Weaker attractive forces, higher vapor pressure. Stronger attractive forces, lower vapor pressure. So we see this kind of opposite effect with that relationship. So that is the last of the properties affected by intermolecular forces. Again, this is going to be on your test. Which of the following molecules would have the highest vapor pressure or lowest vapor pressure? And you'll determine that based on the strength of the intermolecular forces. I hope you guys found this helpful.